Now we study the last question in the exercises for integral. Here the 14. U is C2 in Rn, and the phi is defined as follows. Phi R is omega n-dimensional, the area of the n-dimensional sphere, unit sphere, Rn minus 1. Then the sphere of radius R U d sigma. We know that the area of the sphere of radius R is precisely this number. So the definition of phi R is the mean value of U over the sphere of radius R. Okay, now we have two questions. The first question, as R goes to 0, phi R goes to U0. This is the first question. The second question, suppose Laplacian of U at origin is not 0. Then find the principal part of phi R minus phi 0 minus U0. Okay, this is the two questions. The first question is easy. For A, by mean value, the mean value of U over the sphere should equal the value of U at some point of the sphere. There must be some point UR here, XR, such that the mean value is the value of U at XR. Then when R goes to 0, phi UXR, our UXR goes to U0 by the continuity of U. So this proves the first result, very easy. The more interesting one is the second conclusion. To study the second problem, because we want to find the principal part of a function. Principal part is Taylor expansion. If given you a small function, the principal part or the main part or the main part is the Taylor expansion, the first term in the Taylor expansion. Okay. So for example, if phi R is A0 plus A1R plus A2R. So A0 is 0. But if A1 is 0, then this is not the principal part. But if this is 0, A1, A0 are 0, but A2 is not 0. A2 is not 0, then the principal part is A2R squared. Okay? So this is the principal part. So in other words, we need to study the derivative of a phi with respect to R. So to compute the derivative of phi with respect to R, ddr phi R. But observing the expression of phi, the R appears not only on some expression, but also on the surface, that is the sphere. R is precisely the radius of that sphere. So this makes it difficult to study how the integral, how this part varies when R change. So this is the difficult. But we have a very useful scaling formula for surface integral. By scaling formula for surface integral, what was the formula? The formula for the two-dimensional case, that is n equal to 3. We already studied this. That is the question 4 in our quiz, in our last quiz. But that is also true for higher dimension. Rs f x d sigma equal Rn minus 1 f ry dy. We have this scaling formula for surface integral. The case n equal to 2 has already been n equal to 3 has already been solved in our question 4 in the last quiz. But now we will apply the general higher dimensional case. This will be proved later. Okay, we use this result to solve this problem B. So using this result, our S is apply this result for S to be the unit sphere. Then our phi r would be r to the n minus 1. Then the unit sphere ury, urx, or ury, that is not, sorry, here is the sigma, not dy. Surface integral. So d sigma. Okay. Or maybe I will maybe I deduce this more in more detail. Phi r is 1 over omega n r n minus 1. dBr can be considered as r dB1. The r, what's the rs here? Rs is ry, rx maybe. X belongs to S. Scaling by a factor r. Okay, so the unit sphere is the scaling by a factor r of the unit sphere. That is r dB1. Then our u here, copy d sigma. So by the scaling formula above, we obtain that this is omega n r n minus 1. By scaling, we also have a new r n minus 1. Then the integral is from dB1. That is our S. F r ry or rx, that is not essential. Therefore, the r n minus 1 cancel, which the denominator. We obtain that the result is omega n dB1, the unit sphere, frx d sigma. Okay, so we will use this result. In this result, the variable r does not appear on the integrating surface, integral surface. It only appears on the function to be integrated. So it makes it easier to compute the derivative of phi. Okay, this is the idea. Now, to compute the derivative of phi, let's write phi r is omega n dB1 urx dx. We need to do some preparation. We consider a function. Maybe. Okay, we're taking derivative. If necessary, we consider the function. Taking derivative. The derivative can be taken inside the integral, because surface integral is essentially an n-1 dimensional multiple integral, and for multiple integral, by the question by our previous exam exercises. I have not discussed the exercises, but I provide the proof of the conclusion that for integral which is a parameter under suitable condition, we can taking derivative under the integral sign. Okay, so using the result, actually we can take derivative of the integral by integrating the derivative of urx with respect to r. Okay, so this is true. This is valid. Now, then this by the chain rule, this is just maybe here. This is just 1 over omega n dBr. This is the u prime rx, then inner product with x by chain rule. Okay, or you can write the gradient of u at the point rx, inner product with x, then d sigma. Sorry, this is a surface integral, d sigma. Okay. Now, to continue our computation, we need to consider this function. Vrx is urx. Then, sorry, so many mistakes. This is a unit sphere. So the partial derivative of Vr with respect to xi, obviously this is r di urx by chain rule. And also from this we know that the gradient of Vr at x is r gradient of u at rx. Okay, and then we compute the second derivative dii Vrx. Obviously, taking derivative for this, again, we obtain the second derivative of Vr with respect to xi. By taking derivative with respect to xi, the right hand side gives us another r. Therefore, this result should be r squared dii urx. Hence, the Laplacian of Vr at x is the sum of all the second derivative. So this is r squared Laplacian of u at rx. So we have this relation. Now we have go back to our computation. We have the gradient of u at rx. By our red equation on the right hand side, we see that this is 1 over r. This is r omega n1 dB1 gradient of Vr x inner product with x. Okay. Then we can apply the divergence theorem, because this on the unit sphere, the x is precisely the outward normal vector on the surface. Okay, and because of the norm of x belongs to the unit sphere, so the norm of x is 1, and the direction of x is the point. It is just the normal direction at the point x on the unit sphere. So this can be considered as the outward normal vector. So we can apply the divergence theorem to obtain the r omega n dB, no, not dB, the unit ball, then divergence of gradient of Vr x dx. Then this is the 1 over r omega n b1. taking gradient and then divergent give us Laplacian. So Laplacian VR x dx. But Laplacian VRx is r square Laplacian urx. Using this equation, we can write r square r omega n b1 Laplacian of u evaluated at rx then dx. Okay, from this we see that we have one the r square can salvage an r from the denominator. So we see that when r equal to 0, phi prime 0 is 0, obviously. Okay, so the expansion for phi, the 0 order term is 0. No, the 0 order term is u0. The first order term is phi prime r is 0. So we have to compute the second order term. Compute the second order derivative of phi. We do this in the next page. So phi double prime r would be the derivative of the first order derivative. The first order derivative is here. Phi prime r, we have just computed phi prime r. The final result is here, is r omega n b1 Laplacian u rx dx. Okay, but no, of course this is right, but we don't want to work with this because there is an r here and there is also an r here. Then we to differentiate this, we will have to compute the derivative of the multiplication of two functions, and that will make things complicated. Therefore, we trace back. We don't use this formula. Instead, we use the middle result, intermediate result. That is this point. We go back to this point. We use this result. Okay. So phi prime r. So go back to our computation. Phi double prime r is the derivative of phi prime r. Phi prime r by this result. Phi prime r is 1 over omega n. 1 over omega n. The surface integral over the unit sphere. Gradient of u r x. Inner product which x, then this is phi prime r. Okay, so as before, we can take the derivative inside the integral sign. So this would be 1 over omega n b1 partial derivative of this. But this is just the inner product of this is just I from 1 to n di u r x inner product with xi, then d sigma. The component of the gradient is the partial derivative of u with respect to xi, and the component of x is xi. Therefore, the inner product is the sum of the multiplication of the components. Then this derivative can act on the partial derivative of u. So diu rx is the sum by chain rule again. dij maybe dji, not urx then xg. And by chain rule we have this result. So go back to our computation, we will have 1 over omega n dB1 sum I from 1 to n sum j from 1 to n dij ur x xi and xj and then d sigma. So we let r equal to 0. We obtain the phi double prime 0 is 1 over omega n dB1 I from 1 j from 1 dij u0 xi xj d sigma. Okay. Now we have an important observation. The integral over the unit sphere xi xj d sigma is 0 if I not equal to j. Because the unit sphere is symmetric with respect to xi equal to 0. The unit sphere is symmetric with respect to the plane xi equal to 0. That is the red segment representing xi equal to 0. The horizontal axis represents the xi axis. Okay, and the function is odd with respect to xi. An odd function integrating over a surface, symmetric surface, the result is 0. Okay, so and also we know that the integral of the unit sphere when I equal to j, that is xi square. Xi square, of course, the integral of x1 square equal the integral of x2 square, and equal the integral of xn square over the unit sphere. Now, okay, so using this result, this is the sum of integral x j square j from 1 to n, because every term of this sum equal the integral of xi square over the unit sphere. But this is just 1 over n dB1, the sum of xj square j from 1 to n. But on the unit sphere, xj square is 1. So the result is the area of the unit sphere. That is 1 over omega n. Omega n is the area of the unit sphere. Okay. In other words, we can write dB1 xi xj to be delta ij n omega n. Okay, so our this sum become 1 over omega n dB1 sum I sum j dij u0, then delta ij Kronecker delta omega n over n. And this means when I not equal to j, the term is 0. So the result is 1 over omega n dB1 summing I from 1 to n diiu0 multiplying the omega n over n, then d sigma. No integral anymore. Sorry. The integral have been used to compute the integral of of xi xj, because these are constant, because this integral can move at this place to write integral here. Therefore, in our we do not have integral here anymore. Okay. So we do not have integral there anymore. So the integral can go through the double summation inside the terms. That is the integral which is for integral for xi xj, and the integral for xi xj we already made it clear. So the computation should be I will modify this part, erased, and we have summation. No, summation I j dij u0, then delta I j omega n over n. The omega n will cancel with the denominator, and the sum will be 1 over n sigma I from 1 dii u0. That is Laplacian u0 over n. So this is the final result. So in conclusion, our phi r is phi 0 plus phi prime 0 r plus phi double prime 0 over 2r plus r squared, higher order term, Taylor expansion. Then phi 0 is u0. And phi prime 0 is 0. So in conclusion, our phi r is 2n1 Laplacian u0, because phi double prime 0 is n over Laplacian u, then r squared plus higher order term. This is the expansion of our phi r. Okay. So this proves our result. And also I need to make some correction. We take derivative of phi and r. This is okay, but in fact we don't know whether it is reasonable to take derivative at 0. We don't know whether phi is differentiable at 0. By the definition of phi in this form, when writing phi in this form, we don't know whether phi is defined at 0, or even if it defined, we don't know whether it is differentiable. This is a problem. So principally, we could not compute phi prime r and then let r equal to 0 to obtain the derivative of phi at 0. Okay, this is a problem. It looks like a problem, but this is not a problem, because by this expression of phi, because u is very good, u is smooth, so u is C2. Therefore, from this expression of phi, we know that for every r, phi has second order different derivative. Phi is second order differentiable at every r, including 0. The reason is that u is very good. Okay, so our computation has no problem. Okay.